Okay, so today we will continue to study the clustering, and we basically will cover two clustering methods today. The first one is this NMF, and then the other is spectral clustering. And so, so we briefly went through how these matrix factorization works, and then in the case of a non-negative matrix factorization, it beautifully generates these part-based bases. And then we want to linearly combine them to generate one particular image. But in terms of these linear combination of these vectors, we want to use non-negative linear combination coefficient, which means we do not allow any subtraction from the among these bases. Okay, and then this can be also used in the document clustering and the topic modeling applications. And let me briefly go through what the topic modeling is and how this NMF works. So some of my own students are familiar with these techniques, but yeah, for those who are not familiar with these, let me just briefly go through these how these works. Okay, so in the case of topic modeling applications, we typically start with these bag-of-words vector representation of our input matrix or input data. So this is, the first column is the document 1, and document 2, document 3, and so on. And then the first row corresponds to the keyword 1. Let's see. Yeah, let's call that as term 1, and then the second row is term 2, and so on. And then each component or each element contains the number of frequency of a particular word in a particular document. Right? So this is called a term document matrix representation of our input data as a text document. And then yeah, we can think about this kind of bipartite graph. So, okay, so let's just ignore this part for now. And then suppose this document 1 contained maybe brain and DNA and nerve and organism and so on. Okay, and in this case, in the case of the column vector of this document 1, the corresponding keyword or the term of this brain, DNA, nerve, and organism can be considered as being connected from all these document 1. And then the strength of this connection can be viewed as the number of frequency or number of occurrences of this particular term in this document 1. Okay, so that way we can think about this bipartite graph. What is a bipartite graph? Bipartite graph. Bipartite graph. So the definition of a bipartite graph is, so what is the graph? So graph is composed of basically two types of entities, nodes and edges, right? And then you basically bipartite or partition the node group or the entire node set into two groups. Okay, two groups, and then these edges in our graph is only defined between different groups of an edges, but not within the same groups of same group of an edge. So we can consider in this example, we can consider this entire node set as a union of all the documents. So suppose we have 100 documents and maybe 500 keywords. Okay, and then in total we have 6 different nodes or entities, and then we separate them into two groups of 100 documents and then 500 keywords, and then the graph will contain the edges between these different types of nodes. yeah, such as this, but not within the same group of nodes. Okay, so if we do not, if we can guarantee that there is no such edges within the same group, then we call them as bipartite group, bipartite graph. Okay, so in this case, we do not consider or we do not define any linkages, direct linkages between the documents or the keywords, and so we can view this as a bipartite graph. Okay, and then in this case, we have, for example, 500 different keywords, which is too many. And then each document may contain some edges among these 5 different keywords. And so this topic modeling is actually put some intermediate layer. So the topic modeling can be viewed as a process of creating or generating this intermediate layer, which has a much smaller number of nodes, compared to this 500. So for example, we can, suppose we use 10 different nodes in the intermediate layer, okay? And then we have maybe 10 different nodes, and then each of these 10 different nodes will have a connection with the lower layer of keywords. So this topic 1, among 10 different topic nodes, it will have a connection with the brain, nerve, and neuron. And topic 2 will have a different connections to DNA, gene, and the topic 3 may have a connection of with evolved life and organism. And then the strength of this connection is defined as a real value, but non-negative real value. Okay, how strongly or how closely this topic or this intermediate node is related semantically to each of these keywords. Okay, and then now this document, each of our document is no longer directly connected to so many different keywords, but it is only connected to this much smaller number of intermediate nodes. And so we may have a connection of document 1 being connected to topic 1 and 2, and then their strength is also can be is a real valued real valued strength. Okay, so this is so forming forming this intermediate layers, and then defining or generating or computing the strength from this particular topic to the lower layer, which has a lot of nodes, and then also defining or generating the relationship between this document nodes with the intermediate nodes. And so computing these 2 sets of strengths can be viewed as a topic modeling output. And then from the matrix factorization perspective, so here in this case, and also in this example, we can also view this process as creating some virtual documents of 10 virtual documents additionally. And then using those 10 virtual documents, we want to explain each of our documents. So for example, we have 100 different documents, and then these 100 different documents should be explained as much as possible only using 10 different virtual documents. Okay, and then here in this example, from this typical matrix factorization perspective, so we have 4 different columns, right? And so in this case, we are using 4 intermediate nodes in the middle layer. And then each document or each column can be viewed as one particular virtual document. Okay, and then from the linear combination of columns, this kind of perspective will tell you that using only 4 virtual documents, we have to explain each of our 100 documents by using the linear combination coefficient used here. Okay, so this guy, yeah, so we have a 4 columns, and then this H will have a 500 dimensions with 500 columns with the 4 rows. Okay, and then this, the first row is corresponding to the first document. And then if this this 4-dimensional column was 0.7, 0.2, 0.1, and 0, and then it means it is linearly combining the first column with the weight of 0.7, and the second column or second virtual document with the weight of 0.2, and so on. And so that way we linearly combine 4 virtual documents to create the original first document. And then we use the second set of linear combination columns, for example 0.3, 0.5, 0.2, it's a 0 and 0.2. And then it means we are using the first virtual document by applying the weight of 0.3, and then the second one by applying the 0.5, and so on, to generate the second original document. Okay, so that way these part will specify the relationship or this kind of linkages between the topics or 4 topics or 4 intermediate nodes with the entire 500 keywords. And then this H part, each column will specify, I guess, dirtier, so it specify this. So for example, this weight is 0.7, 0.2, and 0.1, and 0. Okay? So basically the topic modeling can be viewed as computing these two W and H, which is a which forms the matrix factorization of the original matrix A. Okay, so this is a matrix factorization perspective, and then also the topic, another representative method of topic modeling called a latent Dirichlet allocation, or the previous method called a probabilistic latent semantic indexing. So these two are famous topic modeling methods from the probabilistic world, and they have a kind of different interpretation, but the overall or the high-level idea is almost the same. But they are not just using a matrix factorization, but they are using some probabilistic generative probabilistic procedure. Okay, let me just explain that briefly, because yeah, I don't see any reason not to do so. So, in the case of a probabilistic LSI, or probabilistic latent semantic indexing, or latent Dirichlet allocation, so these two methods are representative topic modeling method in the probabilistic world. And then their first step is almost the same. They create these 4 virtual documents. Okay, but each document is represented as a particular probability distribution. So if the first document or first virtual document is about some science document, and then it will have some high probability corresponding to soccer and basketball and so on, but very small weight. No, I mentioned it as a science topic, and then the soccer and baseball will have very small weight or small probability of observing that particular keyword in this science kind of a virtual document called a science. Okay, so it's about, yeah, it's like creating this virtual document called a science, and then you would have a small weight on these unrelated terms, but the high weights on maybe material sciences and maybe computer science, and those related terms will have a high chance or high probability of observing that particular keywords in this topic. Okay. Okay, then Yeah. Then this topic, yeah. So we have a 4 different probability distribution. So we have a virtual document called a science and sports and maybe some business and some other high-level topics. And then in order to, yeah, and then let's when thinking about a particular document. So the first document may be just a purely science-related topic, or maybe a sports-related topic, or maybe it can be a kind of a mixture of these. So one document can be can discuss maybe 60% of the science topics and 40% of the sports topic. Okay, yeah, we can think about this kind of mixture of those topics for one particular document. So in this case, okay, this H part or this linear combination coefficient will have maybe 0.6 related to science, and then 0.4 0.4 of one weight related to sports topic. And then we can think about the mixture of these two. So we can just simply linearly combine these two probability distributions with these weights. Okay, and then we can sample. Yeah, we can have a linearly combined probability distribution over keywords, and then we can think of generating one particular document from this mixed or linearly combined distribution over keywords. Okay, so in this case, suppose we had, in our the first document we had maybe 5 different keywords. So it's like I study math and maybe sports analytics. Okay. So in this case, we look at the probability of generating this keyword I from this aggregate or linearly combined probability distribution. And then we can also pick up the probability of generating this study and math and sports. And then we just simply multiply all the 5 probabilities together, and that can be viewed as a likelihood probability of generating this document from our linearly combined probability distribution over keywords. Okay, and then we can optimize these linear combination coefficient as well as our pseudo documents. Okay, so this is how we interpret this topic modeling from the probabilistic work. We basically generate each keyword from some distribution over keywords, and this distribution is basically a linear combination of several different distributions corresponding to different virtual documents. Okay, and this is a kind of simplest way of generating these keywords, but in fact, PLSI or probabilistic latent semantic indexing or latent terrestrial location, their generative process of generating each keyword is a little bit more complicated. So it is not linearly combining different distributions of keywords in advance. So previously I described the process as first linearly combining those 2 probability distribution over keywords, right? But we do not do so. We actually pick in our generative process, we first pick up one topics among the 2 with the probability of 0.6 and 0.4. It's almost like a Gaussian mixture model. And then once we pick up one particular virtual document, and then we follow the probability distribution of that particular virtual document to generate each keyword. So when generating I with the probability of 0.6 and 0.4 of picking up one among the 2 probability distribution. Suppose we picked up the first one, and then we look for the probability of generating the keyword I. and then that's the probability of generating the keyword I, and then suppose, let's move on to the second word, and then we also go through this sampling process or selecting process between these two distributions with these two probability, these are prior distributions. And in this case, although the probability was small, like a 0.4, this time suppose we picked up the second topic, and then we just to follow this second distribution over keywords, and then we look for the probability value corresponding to this source, and then we can still combine. We can still consider generating each keyword. The case of an or steps of generating one keyword at a time. But for each generation, we go through the sampling process of particular topics with this prior distribution, and that way we can compute the overall likelihood function, and we want to maximize this likelihood function. So this is how we formulate and then build some algorithms for generative topic modeling process, or in general, most of these generative probabilistic models are going through this type of process. Okay, so we first generate some variables or some topics first, and then in the next step, we generate the next random variable from the distribution. That's determined by the first sampling process, because we first picked up the topic, and then this topic will give us a particular distribution over keywords, and then from this distribution we sample or we pick up the word, which is the second or the next random variable. So we go through this sequential generative process of basically generating or sampling or picking up those random variables. So this is a kind of typical story of generative probabilistic models. Okay. Any questions so far? 네. 노멀라이즈? 언제요? 이 NMF 아니면? Yeah, so the question is about how to normalize our input matrix or input term document matrix. So in this matrix factorization, so for example, when applying NMF or non-negative matrix factorization to compute the topic modeling, and then we can consider additional pre-processing step before running this topic modeling using NMF. So sorry for keeping using this small figure, but one typical way of pre-processing is to normalize each column. So we just normalize each column to have unit Euclidean length or unit L2 norm. Okay, so in this case, if one document was really long, then it will have many non-zero or large values in many of different dimensions or corresponding to different keywords, and so on. But the second document was only composed of maybe 3 keywords. I went there. Yeah, composed of these 3 keywords, and then in the corresponding keywords, it will only have maybe just one. So apparently the first document will have much larger lengths. Okay, so in this case, in order to reduce this unfair effect or unfairly large effect of the first document, we can normalize this so that their L2 norm becomes just 1, and then we go through the same normalization process on the second document. or optionally we can do L1 norm regularization. So for example, we just simply divide each column by the total sum of these values. Okay? In that case, the sum will become all 1 for each different column. So in this case, it can be more similar to the notion of distribution. So if we view each column or each document as a distribution over keywords, in this case, it will make more sense to just normalize based on L1 norm. So we can apply this kind of idea when running NMF as well. So L2 norm or L1 norm normalization can be adopted. And then also, additionally, we can do additional normalization such as TF-IDF. So TF-IDF is another kind of a pre-processing step that boosts up those rare keyword, the frequency of rare keywords. Okay, so in this case, it is not about the column-wise normalization. It is about the row-wise normalization, right? So why is it row-wise normalization? Why is it row-wise normalization? So the main idea is when doing the L1 norm or L2 norm normalization on each column, when normalizing the first column, the second to the rest of these columns will not affect on how we normalize the first column. But in the case of TF-IDF, what we are doing is we look at each row. So for example, some keywords like high was appearing many of different documents. And then in this case, we view this keyword as not very meaningful or not very informative because it appeared anywhere in our document corpus. So it does not characterize much particular document, right? But in some case of, in some keywords of maybe chemical, so it will appear only on those documents that are highly professional or highly relevant to this specific topic. In this case, we can think about this kind of document frequency. So high, appearing in many of the documents, we will have a high document frequency. So among maybe 100 documents, it appeared maybe 70, and then this keyword appeared only 10 documents. In this case, even though this keyword high appeared only once and the chemical was appearing only once, but the importance can be different because this chemical will have much more meaningful information. So we boost up this rare keywords, okay, and then we decrease the weight of this frequently appearing keywords weight. So in this case, we consider this the patterns of these appearance of each keywords throughout different documents. So that way, we consider it as a row-wise pre-processing or row-wise normalization or weighting. Okay, and then in the case of an NMF for topic modeling, there is no right or wrong answer about which pre-processing step that we have to do, but we typically do not do this TF-IDF. And also, we usually do L2 normalization in the case of an NMF. But what about LDA or PLSI? In these cases, we do not do any of these pre-processing in the case of generative probabilistic generative models. So we don't usually do TF-IDF, and also we don't do this L2 or L1 norm regularization. So I'm gonna skip the explaining the detailed reason for why. about this not using pre-processing, but in the case of an LSI or PLSI, if these values becomes non-integer, so once we divide each values by their L2 norm or by applying a TF-IDF, we'll change all the integer values, which was just a frequency. I mean, they change these integer values of a frequency into some real values, right, as a non-integer value. In this case, this generative model will not be applicable because, as I mentioned, each keyword will be generated from this sampling process of a particular distribution. But how can we generate maybe 1.3 amount of samples? Okay, so we can only generate these integer number of samples, but not real valued samples. So that's why we cannot easily apply this TF-IDF or L2 norm normalization and things like that in the context in the case of an LDA or PLS. So yeah, so we don't usually do any of the pre-processing step other than just the stop or the removal. Any other questions? Okay.
I think this is frequency-based instead of any logarithms. So this doesn't consider the context. For example, the word with multiple meanings, but this cannot consider using bag of word or can't find it. Just use some frequency on the certain word.
Right.
It does not consider some context word.
So you're talking about some polysemy issue, like the same word can have a different meanings.
And order of the word.
Order of the words. Yeah, right. Yeah. So both. Yeah. So the topic modeling methods, by default, they only utilize this unigram information. They do not. They throw away the information about the ordering of these keywords. So, for example, I support the president's decision, which means I agree, and yeah, you guys know the meaning, right? But what about maybe support vector machine? So the support vector machine, although the meaning of this support, yeah, is also like this kind of supporting this hyperplane or separating hyperplanes, but those two keywords may have a quite different meanings. So in order to distinguish different meanings, we may have to consider different orderings and also maybe some phrase information as well. So instead of only using maybe unigrams of support, vector, and machine, and also decision all separately, we can instead construct our dictionary by incorporating some bigram or trigram and so on. Okay, so support vector machine, possible dictionary size of a bigram. It will be like this. Okay, so it's roughly 500 squared. And then in the case of the trigram, which is composed three keywords in a particular sequence, we will also have maybe 500 cube, right? So this is a practical problem, and also you can think about the sparsity. So the sparsity means the fraction or the ratio of non-zero elements among these matrix elements. So if we have a 500 keywords and 100 documents, and then the sparsity or the sparsity degree or the degree of sparsity, or maybe we can define the sparsity score as the fraction of non-zero elements out of these entire elements in our matrix. So it can be maybe 5%, and it means among the 5 elements we approximately we observe 1 non-zero entries and 4 zero entries. right? Oops. So in that case, it will have a 20% of sparsity. So usually this term document matrix is really sparse, which means this rate of sparsity will be really low. Okay, but if we incorporate the bigram and trigram and so on in our dictionary, we have no problem. I mean, as long as we have a sufficient amount of a memory or hard drive, and then we will have no problem by just keep editing additional dimensions. But overall, the sparsity will be even lower, because maybe when just counting the occurrence of a support, and then it might be frequently appearing, but what about support vector? I mean, what about the probability of observing support vector? Okay, it will not be observed in maybe I support your decision or something like that. So in this case, this kind of particular combination of support and vector will have much lower probability. And thus, overall, the sparsity value, score or degree of the sparsity will become lower and lower. And this in particular will cause some problem in many of these algorithms. So if your input matrix will become sparser and sparser, and then in general, you can think of it as increasing the probability of messing up your algorithm or the result from your algorithm. So when running LDA, if this sparsity becomes really low, and then your result might not be very high quality. Okay, so this particular problem is also appearing in just a unigram kind of applications, especially when using short text. So I once worked on some topic modeling on the Twitter data, for example. So as you guys know, the Twitter data has the character limit. So one document should have up to 40 or 400 characters, okay, at most. And so each document is really short, which means one particular column will have a very small number of non-zero values, and thus, in general, compared to the corpus composed of large length, lengthy documents like a lengthy Wikipedia web pages forming one document. I mean, in the case of a Twitter data, the sparsity will become very low, and so if you run the topic modeling on these documents, then the topic may not make much sense. Okay. Okay, and then back to this bigram and trigram. So you can this has its own problem of exploding dimensions, and even lower sparsity score, which is generally bad. But you can be more creative, and you can kind of more you can be smarter in constructing your dictionaries. So when constructing bigram or trigram, you don't need to involve or add all the possible bigrams. So you only accept those bigrams that have at least a certain amount of a frequency. Okay, so in the case of support vector machine, you observed this particular phrase at least maybe 50 documents. Okay, it means out of 100 documents, at least 10% of the document contain the support and vector. So it can be viewed as a document frequency. So this document frequency is at least over a certain threshold, and then you accept or you register this support vector as a bigram in your dictionary. But in the case of support your, so suppose you have one document having a sentence of I support your decision, and so you try to register this support your as one bigram in your dictionary. But suppose you only observed only one document out of 500 documents. In this case, document frequency of this particular bigram will be really low. And in this case, even though you observed this particular bigram, but you don't register it in your dictionary. So that way you can kind of maintain at least a certain level of sparsity in your term document matrix representation. So in this case, you can kind of apply this kind of a little bit smart criteria when registering this bigram, and also you can apply this kind of criteria into registration of trigram as well. So in the case of trigram, possibly there are so many different combinations of trigrams, but you only accept those trigrams that have at least above a certain threshold of a document frequency. And this kind of process is also applied in the recent machine learning or deep learning methods as well. So yeah, with some of my students, I studied some papers about character level language modeling or kind of NLP or natural language understanding tasks. So the typical starting point in handling the text data in the deep learning is to construct this unigram dictionary. Okay, unigram dictionary, and then for example, pre-compute and pre-register. Okay, so in these two keywords, they are certainly two different keywords, and so each will form one particular dimension in our unigram dictionary, right? But we can be more creative by just applying a character level dictionary. Okay, in the case of character level dictionary, in this case, one unit was one word, but in the new case, we are considering one particular character as one unit of an information. So this one was one single word encoded in maybe 500 dictionaries. But now we view this as this, a sequence of like 26-dimensional vectors. So it is quite simple. So we have 26 characters in alphabet. So our dictionary will become now 26 dimensions. And then we typically use a one-hot vector for this, a P and R and E and so on. Okay? And in that case, I pre-compute the algorithm. So in this case, each keyword will have a one-hot vector originally in the 500-dimensional space, where different by just using unigram dictionaries. But now this one is composed of maybe this first character represented as one-hot vector in the 26-dimensional space, and then this space, we just skip them, and then P will be also another one-hot vector in the 26-dimensional alphabetical dictionaries. Okay, so in this case we will only use 26 dimensions in our dictionary. But in this case, it is not very good model because it is not directly considering the sequence of maybe pre-compute and things like that. So different keywords should be treated differently. But in this 500-dimensional size of a dictionary, different sequence of different characters, okay, they will be treated as a different dimension or different information. But in this character level encoding, we are throwing away these different distinct word level information. Okay, so in this case, we are only using 26 dimensions, but we keep adding our vocabulary or dictionaries so that we incorporate bigrams or trigrams that have higher that have a higher number, higher degree of frequency in our document corpus. So if we often, or if we frequently observed this is a sequence of a PRE, and then it can be considered as a trigram, right? Even though we started from the unigram of each characters, but now we are considering this a trigram, okay, that have a particular sequence of those three characters. In this case, if we observed the number, if we observed the frequency of this pattern at least above a certain threshold. So, for example, among maybe 10,000 words in our document corpus, we observed maybe 100 different number of occurrences of observing this particular character sequence, and then we add it to our dictionary. And then now, apart from very simple dictionary at a character level, unigram characters from A to Z, we now add additional dimensions corresponding to PRE. Okay, so that way we incorporate unigram characters and also bigram and trigram and so on, all of these character level sequences that have a high frequency of observing these character sequences. So that way we can dynamically add our dictionaries or dimensions. So this kind of character level starting point, I mean pre-processing is also quite often used in these days NLP techniques typically using deep learning. Okay. Yeah. So this is my kind of naive idea, but let's imagine this. So sorry for bad handwriting, but it's in Korean. But this two different words will be forming a different or distinct dimensions when using a word level dimension or dictionaries, right? So in this case, even though our word embedding may encode those two keywords similarities to be really similar to each other, but in general, those two, our very first starting point of using a word level dictionary as a one-up vector among our entire word level dictionary is saying that those two keywords are quite distinct, just like other keywords like maybe the distinctiveness or differences between those two really different keywords, and the difference between these two keywords will be the same in the very beginning. But if we use a character level encoding to encode each two different words, and then they will have a very small differences at this part, right? At this part. So that way, from the beginning, we can kind of catch or capture these slight differences and maybe large differences between different words in our maybe NLP model. Okay. So I'm not sure if I explained properly, but this is a kind of potential advantages of using character level information. And also, I think this is a more kind of closer to kind of true end-to-end setting or end-to-end the paradigm of a deep learning, because word level starting point of using a word level encoding is not really true end, because we are also we can also decompose each word into character level, which are more lower end input, which is closer to real ends of our input information. Okay, any questions so far? Okay, and then using the topic modeling with the non-negative matrix factorization, we can also visualize these results by using the topic modeling as well as a 2D embedding that we studied. And then this is one example of my own research, but I will just skip them. Yeah, I'll just skip most of the details, but let me try to briefly explain what this is about. So this is a one kind of a version. I mean, one example of making the topic modeling process as more interactive. So interactive means user wants to do some additional thing on top of this original topic modeling process. So we have this original topic modeling using NMF. Given the matrix A, we are trying to obtain W and H. Yeah, similar to this. Okay. So we basically want to minimize the difference between A and the product of our output matrix W and H. And then now let's consider these two additional criteria, which work as a kind of regularization, or it also works as some channel or the means of applying the user inputs. Okay, so here, you can understand it as follows. So we have W, which represents this virtual documents. Okay, so virtual documents is one set of variables that we want to compute from our topic modeling. But suppose you want to make this output matrix W to be similar to some additional matrix that we call W reference matrix. Okay, so in this case, so in the first virtual documents about science, the topic modeling result gave you the weight of a keyword, maybe chemical, as 0.7, and maybe baseball as 0.2. So it means there exists some relevance between this science-related virtual document to this keyword baseball. But we want to make them directly as 0. And then we can set our reference matrix WR. So this is an additional input matrix. So yeah, please note that this matrix is our output that our NMF algorithm is computing, but we are giving additional input that is the same size as a W, but in this place corresponding to this baseball, we are giving the explicit input as 0. Okay, and then we just consider the difference between this output that NMF generates and also our input. Okay, input kind of reference matrix for our topic. And in this case, if we consider the optimization process of this W part, and then W part should minimize this part, but at the same time with the weight of an alpha. For example, alpha was set as 0.1. And then we consider the difference generated from this part, okay, 0.2 and 0, which is clearly like creating the difference of 0.2. Okay, so this point is discounted by the weight of 0.1. So 0.02 was participating or contributing to our loss function. So W should minimize this part as well as it also has to focus on minimizing this loss as well. Okay. Okay, so this is the role of this WR, and let me ask the question at this point. Then, okay, then what if we want to what if we want to supervise or give a user input about this reference on the first virtual document, but not on the other 3 documents? So we don't want to give any information about this. We don't want to additionally supervise the letter 3. We only want to supervise on the first column. In this case, what we can do is that we want to apply this masking matrix where it's like we have I'll just draw new matrix. So suppose we have 4 matrices, there may be 6 terms and 4 topics. And then we have the same size of a matrix. And then we are multiplying 4 by 4 matrices that have the same size of the topics in both rows and columns. Okay, then because we are multiplying this matrix on the right, and then let's think about the diagonal matrix to be multiplied on the right. So this is diagonal matrix. And then suppose we set our diagonal matrix as this 1 0 0 0. Okay, and then in this case this 1 will be applied to the first column. So overall this will generate some difference matrix. So we just set some garbage values in this part. Okay, and then with this meaningful input that we actually gave to the algorithm, so that the relevance to this baseball term from this science should be 0. Okay, so that was 0. Then that corresponding output was 0.2. Then this part was 0.2, right? And then this part will be filled up with some garbage values. And then we are actually multiplying this matrix of 1 0 0 0, and then this will be multiplied like a column wise. And then the resulting matrix will make all this garbage part to be 0, right? And then preserve the first columns as it is. And then if we compute their Frobenius norm, then we can make the difference of the columns that we only supervise. Okay, we can make this column that we selected to contribute in our loss function. So that's why we kind of incorporate this kind of masking matrix. Okay.
저건 정방향별로 만들어야 되는데 원바이 N4바이로
이걸요? 4x1로?
4바이 4
이게 4x1로 하면 네. 4x1로 하면 네, 4x1로 하면 so the question is what if we just use just one single column, because because these 3 parts will be anyways multiplied by with the 0. Okay? In this particular case, you're right. We can only it is no problem to just use the first column. Okay, but what if we directly what if we want to supervise the first and maybe third column? Then in the case of diagonal matrix, the value will be 1 and 1. In the case of using this diagonal matrix. But if we use this a single column, then the single column will be 1 0 1 0, right? But in this case, it is actually linearly combine the first and the third column into one single column. But if we had maybe 0.3 and 0.1, and we want to directly supervise the first and the third column, and then if we are gonna use this guy 1 0 1, and then before computing the squares, we are actually linearly combining them into single value 0.4 and maybe 0.2. So in this case, before taking the squares, we are adding them first and then taking the square. But we want to compute the summation, the squared summation of each of these values. So we want to make them as different or separate columns. Okay, in this case, what is the problem? I mean, can anyone point out one kind of potential limitations? So in this case, by having this diagonal matrix on the right, so we can pick up. So we have a capability of picking up those columns that we want to directly supervise, right? So if we selected the first column and then we can set it up as 1 0 0 0. But if we set 1, so suppose you want to directly supervise on this guy, because this guy was this the keyword about the baseball. So you want to supervise this value in particular, but so that way we set this value as 1. But what about this? What about this value? So you want to supervise this as 0, but you sometimes you didn't want to care about this value. Okay, so for example, this was a baseball, and then this was maybe something like high. So this guy can be directly supervised as 0, but sometimes we may not want to care about this value explicitly, right? But in this case, we have to supply, or we have to provide some value, or we have to provide this entire columns. And so we have to specify this value explicitly, right? So we have no choice of selectively choose a particular dimensions or particular rows, right?
그 마스킹하는 매트릭스를 4 곱하기 4로 잡지 말고 6 곱하기 4로 잡는
6 곱하기 4요?
바스켓으로 들어가는 곳에만 이제 1을 넣고
근데 이제 여기서 6 곱하기 4는 안 되고요.
그러니까 엘리먼트 와이즈 하는
네, 맞아요. 네. Okay, so I think the student's answer was correct. So in case we want to supervise a particular element, not the entire columns, and then instead of just a matrix multiplication, we can introduce additional operator or maybe element-wise multiplication, and then our matrix will have the same size as 6 by 4, and then we can set the corresponding element by 1. Okay, and then and then all the other values as 0. Okay, so that way we can think of this masking by using element-wise multiplication. But at the same time, so when designing your own algorithm in your own research, I mean, especially when playing with these linear algebraic tricks, you have, so there is a two-part of, in your research. So the first one is to create this formulation, objective formula, okay? So you can build your objective formula by using your creative mind, but also the second part is actually to derive or develop some algorithm to optimize your own objective criteria. Okay, so in these two, in this perspective, it may be often the case that sometimes it is quite easy to develop the objective formula, but it is sometimes difficult to um, develop this updating formula or this optimization algorithm to uh, optimize your own objective criteria. So in the case of a gradient descent, almost all the case, it is almost always possible to create your updating formula or optimization procedure. But if you are using maybe second order, or if you are using some constraint optimization, and then your updating algorithm may be a little tricky, and sometimes it may be impossible. So in that case, you have to go back to your own criteria, and then you may have to change it so that its updating formula can be easily derived. Okay, so in the case of an NMF, so the frequent optimization criteria is using this Frobenius norm, this kind of Frobenius norm, and also KL divergence as well. But you can imagine like a L1 norm or maybe L3 norm, and so on. Right? So by using different different mathematical norms, you can define your own objective formula. But sometimes, in some cases, it's not even possible to derive the updating formula or the optimization algorithms. And then in that case, you have to go back to your own objective formula, and then you have to see if some other alternatives can make it possible to derive the updating formula. Okay, and then let me just finish the later explanation about this part. And this is about the direct supervision on the H part. So H part was about this. So if we had a maybe sports-related topics and science-related topics, and then the algorithm is saying that the first document was about 60% of the science and the 40% of the sports. Okay, but we want to make our topic or directly related, purely related to the first document, so that like 100%, like 1 and 0. So in that case, our first document was originally a mixture of the two topics, in science and sports. But we actually want to set or create one topic that is like just as a mixture of maybe the first document that is originally a mixture of science and sports as our own one topic, because that is some meaningful topic to us. So in that case, we can we can kind of supervise our topic so that by manipulating this H part as well. So instead of 60% or 40%, we change it as 100% and 0, and then this virtual document will be created accordingly by following this kind of contribution from the first document. So in this case, we can also supervise this H by using HR, or reference matrix for H, and then in this case I use the masking matrix on the left, which means we are applying the masking on the left, which means we want to directly supervise the particular row. So for example, in the case of first topic, we want to have a pure contribution from the first document. But in the case of the second document, we want to have like a zero contributions or zero relevance to the same same topic or virtual document. So that way we can have like the first row in H as a cluster indicator. So this document, and this document should be completely belonging to the first topic, but the other documents should not be affiliated the first document at all. So in this case, we can manipulate this kind of particular row corresponding to the particular virtual document. Okay, so that way we have this masking matrix on the left. Okay, so yeah, so some students might have no idea about what I'm talking about. If they have not much linear, they don't have a much linear algebraic background. But if you guys have some linear algebra background, and then I think hopefully you have some understanding about what I mentioned. Okay, so let's have a maybe 5 to 10 minute break, and then continue after that.
조금 교수님하고 김성 교수님하고 이름을 까먹었는데 한 분 계시잖아요.
하정우?
네, 하정우. 그래서 아직 수정을 조금 하긴 해야 되는데.
아, 그분만 봐요?
아니요.
그냥 오픈 세미나죠?
네, 근데 일단 녹화를 하니까 이거 그때 이거 뭔가 엑스퍼타이즈보다 그렇게 하면 뭔가 제가 뒷면이 전문가처럼
엑스퍼티즈도 괜찮아요.
인터레스트 정도 해도 괜찮죠.
그렇죠.
그다음에 이거 참고하는 거 앞에다가 써놨어요. 그다음 앞에는 그냥 쭉쭉쭉쭉 넘어가고. 이런 거 좀 그림 하고 있거든요.
네.
근데 이거는 이제 제가 한 거를 중간에 넣을지 아니면 끝에 몰아서 넣을지 임팩트 있게. 근데 중간에 넣으면 약간 흐름상을 설명을 할 때 편하긴 하거든요. 뭐냐면 LS간에 한번 직접 구현해봤더니 하면 설명하면 되고, A 시간 같은 경우도 이게 원래 기존 멀티태스크 러닝을 하는데 진짜 가짜 맞추고 클래스도 맞추고. 네. 제가 이렇게 바꿔서도 한번 해봤다. 그런 걸 그냥 얘를 설명하면서 하면은 훨씬 더 수월하게 넘어갈 수 있긴 한데, 뭔가 끝에 몰아놓는 것도 더 좋을 것 같기도 하고.
그냥 중간중간에 넣는 게 좀 더 좋을 것 같아요. 그러니까 좀 더 강조하거나 좀 부각해서 보여주고 싶은 거는 나중으로 미룰수록 안 좋아요. 미룰수록 어텐션도 떨어지고요. 네.
네. 그 다음에
왜요? 간단한 거요? 네.
그 컴퓨터 도착했다고 하는데 그래픽스 연구실에서 어떻게?
뭐요? 뭐 우리가 갖고 와서 거기에 리눅스를 깔아서 그 컨셉 벡터 거를 좀 셋업을 한번 해보면 될 것 같아요. 네. 한번 좀 깔아봐 줄래요?
그거 어디로 가고?
그거요? 일단은 일단 연필학생 자리에서 뭐 해보고 그냥 랜선은 뭐 꼽아서 한번 작업을 하고 준비되면 이제 영빈 학생한테 얘기를 하면 그걸 또 저쪽으로 가져가려고 하는 이게 시기가 언제 될지 모르겠는데. 네.
근데 그 컨셉 벡터 그쪽을 모르겠어요. 데이터베이스 연동.
그래요? 거기 어디 안 되면 좀 그거 뭐 에러 메시지나 그걸 나한테 보내주면 내가 해결해 줄 수 있는 건 내가 하고, 아니면 뭐 저기 덕근 형이랑 이야기를 해갖고 한번 해결해보자. 네.
그리고 이론적인 거는 일단 뺐어요. 그게 원래 이론적인 것도 계속 김수홍 교수님이 이론적인 거 하면 좋겠다고 했는데 빼는 게 좀 좋을 것 같아요. 이렇게 그냥 한 줄로만 한 슬라이드만 넣고 나머지는 다 어펜딕스에다가 다 넣어놨거든요. 그래서 이렇게 조금 더 좋을 것 같아서 어펜딕스로 다 빼놨고, 이거는 어펜딕스는 발표 때는 안 다루려고 하고, 그 다음에 이제 그러니까 앞에 거까지 하면은 솔직히 뭐 퀄리티 있게 만들긴 했는데 기존 거랑 크게 차별성은 없어서 뭔가 이제 future of 간 해가지고 여기서 좀 제가 생각하는 간의 미래 그런 걸 좀 담아달라고 하시더라고요. 제가 한 것들 또 주면.
Okay, let's continue. There are some variants of this NMF because it's personally it was my one of my main research topics, and so I try to improve it so that I can be more flexible to incorporate the user inputs. So in general, they can be viewed as a kind of user-driven machine learning or semi-supervised machine learning, where we can incorporate additional knowledge into these models. Okay, but I'm gonna skip those examples and then move on to the last part or the next algorithm called is spectral clustering. Okay, spectral clustering. So in the previous lecture, I once mentioned about this word spectral. So spectral typically involves eigen decomposition. Okay. So this spectral clustering is also involving this eigen decomposition method as a main algorithm. But under the hood, it has really nice theory from the graph theory. So we will study a little bit about it and then understand how this spectral clustering works. Okay, so mainly this spectral clustering takes an input as a graph form instead of feature vector representation. So in one type of input of our clustering algorithm is this feature vector representation, where each column is one data item and each row is one feature or one dimension. But now we can think about alternative form of an input where we have this square matrix. So if we have 100 different items, and then we can think of this square matrix of 100 by 100, and then I comma j will specify the similarity between i's component and i's and j's data items. And those the form of a graph input is quite available in many different applications. Hyperlink structures among the websites. So if one website has the link to another website, and then we can view that as a kind of edges between one website to another website. Okay, so in this case, we can view them as a kind of high similarity between these two. And also the friendship networks in social networks and citation and co-associate graphs, and also can be viewed as a graph input. And then so typically in the case, if we have, originally if we have this feature vector representation, and then we can convert them into a similarity graph form of input information. And then similar to what we used in SNE or TSNE, we can use this Gaussian kernel. So if we had a two feature vector between I comma j, i's data item and j's data item, and then we can first compute the their Euclidean distance, and then converting them using this formula, which is a Gaussian kernel. And then we can, this function is like monotonically decreasing function. So if distance gets larger, then similarity becomes smaller. And that way, if we have 100 different data items, and then we can compute each different pair of these distance value, and then the similarity value. Okay, then we can interpret this pairwise similarity matrix of maybe 100 by 100 as this weighted graph. So between the first and the second data item, the similarity was computed as 0.7, 0.8, and 0.1 between 1 and 5. Yeah, that way we can we can interpret this pairwise similarity matrix into this graph form. Okay, and now in this graph form of an input, our clustering in this graph, the objectives of this clustering in this graph can be viewed as cutting these entire graph into multiple pieces. So if we have this kind of graph, so in general this graph is connected to between different data points, and doing the clustering means we are splitting them into multiple groups, and then when cutting them into multiple pieces, there should be some involved edges, okay, that were cut after separating them into multiple groups. And then we can think of these summation of these cut edges as our loss function. So in this case, we had to pay the price of maybe 0.1 plus 0.2, right? So if this price or this loss value is larger, and then we didn't do very well in this cutting into multiple pieces, which is the clustering process. Okay, so this graph cut is exactly this kind of notion, and our objective function can be viewed as this, minimizing the ways that were actually cut or that were involved in this cutting process. Okay, and then we can just simply minimize this kind of cut, measure, and this is called a min-cut algorithm or min-cut criteria. But in this case of min-cut criteria, this is not a good algorithm in general, because it can generate or it can produce some undesirable clustering result, so that one of these groups may have really small number of data points, or the small number of nodes. Because if we cut this entire pieces into this one and the other groups, in this case, since we have only one edge in the first group, and then naturally the edge starting from this node will be fewer. Okay, we'll have a few number of edges, so it can naturally minimize this cut measure. So in this case, so it will typically generate this imbalanced size of cluster results. So in order to compensate this undesirable effect, we can think of this improved measure called a normalized cut. And this is the main criteria that we focus today. And this is this normalized cut has this kind of definition. So we still use this cut measure when cutting the entire group into two pieces, two groups of nodes. So we have node set A and node set B, and the cut measure is the total sum of involved edges, right? And then instead of just using this cut measure, we actually divide this cut measure by the volume of A. Okay, so the volume of A, what is that? So this volume of an A can be simply defined as the number of nodes. Okay, so in this case, if we cut them like this, and then even though we have maybe very small edges, 0.3, 0.1, 0.4, and then it has only 3 edges. So in this case, if we cut them in this manner, and then there may be many edges going through this cut. So that way it will naturally have more number of edges. But now, instead of just computing the total sum of edges, we can just compute the average number of edges, or average number of average weight values. So in this case, since we have only one edge, since we have only one node, the total sum of, or total cut measure, 0.3, 0.1 plus 0.4 is divided by 1. But what if we had maybe 4 nodes in this side, and then it will be divided by 4. So that way we can kind of discount, or we can properly decrease this cut measure by the number of nodes. And then we have 2 groups, one here and then the other in the other side. And so using the same cut measure, we can divide it by each volume, the volume of each group, or volume of the first group and the second group, and then we just add them up together. Okay. Okay, and then the other, another more advanced definition that we can think of about this volume of A can be also can also become this guy, the total weight of an edges originating from the group of an A. So the first idea is to use the number of nodes inside of a particular group, and the other idea, which is a more advanced idea, is considering the total number of total edge weights originating from this particular group. So the main idea is, so you guys know, you guys now understand the meaning of, the notion of cut measure. So cut is incorporating or considering the edges only crossing this boundaries, but we make this measure as a kind of relative measure. So suppose like those parts of an edges were in total 0.7. Okay, so this is a kind of absolute summation. But when looking from this group, suppose these edges inside of this same group, the total sum of an edges were maybe 2.4. Okay, or the total sum of the edges inside this group was maybe 0.5. In this case, 2.4, 0.7 over 2.4 and 0.7 over 0.5. So it will properly incorporate the edges, the average strength inside of the group and average strength going outside of the group. Right? So, in other words, we can think of the total edge weight or edge strength inside of one particular group, and then outside of these groups, originating from the same group. Okay, so that way we can consider these two types of edges: intra edges and inter edges, starting from the same group, and intra plus inter so this inter edges are corresponding to cut measure, and we divide it by this intra plus inter edges, and that way we can properly normalize this cut measure, and this is called a normalized cut. And keeping that in mind of intra plus inter edges, so that is corresponding to this, the total edge weights originating from the group A. So that is the definition of volume of an A. Okay, volume of an A. Okay, so again, if A had 3 edges, and then regardless of any cuts, we consider all the edges originating or starting from those three nodes. And then we just compute the total sum of an edge values. Okay, so this is the definition of a volume of an A. And then among all these edges, there will be some edges involved or going through this boundary that we use as cut, right? And then what is the fraction or what is the ratio between those edges actually going through our boundary over the total amount of an edge weights. Okay, so this is the normalized cut, and if we separate them or if we split them into two groups, and then we have these two sides, and so we just simply add them up to compute this normalized cut between the group of an A and group of B. And what about what about having like three groups, A, B, and C? Suppose we had a number of clusters as 3. Okay, then this measure is not pairwise measure. Okay, so it is so you can easily compute this as maybe this one group and the second group and the third group. Okay, and then you can easily extend it to more than two groups. So what is the normalized cut for this group? You consider all the edges starting from these nodes, and also it will have the nodes inside the group, and that way you compute the volume, and then you also compute the edges that goes through the boundaries, okay, boundaries of that group, and then computing that ratio, you can compute the normalized cut for each groups, regardless of the number of groups. Okay, so minimizing this normalized cut is called this normalized cut algorithm, and this has been quite a popular clustering method, especially effective for image segmentation. Yep, so you guys know what the image segmentation is, right? So given one particular image, you are actually clustering your pixels into multiple different segments, okay? So it's like one cluster here, then the second and the third cluster, and so on. So it's like segmenting or clustering entire pixel regions into multiple regions. Okay, and in this case, so this is a normalized cut algorithm result. So n cut is normalized cut, and then back to our slide. How can you first construct? This kind of graphs? So what is our data item? So the data item is our pixel, right? And then what is the similarity or the distance between the pixels? How can you define the similarity of the pixels? Feature, or someone else? RGB? Yeah, right. Yeah, so we basically design some features that describe our pixels, right? So one obvious feature vector or features could be the RGB values. So we now already have like 3 different feature values. And then what else? Can we incorporate some other pixel values? And so let's imagine we only used pixel values. And then in this case, one interesting property in this image segmentation is that these entire regions were clustered into one single cluster. So it maintains a little bit of a spatial continuity, right? So it didn't like segment, okay, this pixel should be the first cluster and the adjacent pixel should be belonging to the second cluster and so on, right? So it at least generated this chunk of regions as one single cluster. So how can you make your algorithm work that way? So what kind of what other features would you incorporate in order to encourage this kind of behavior in your algorithm? Gradient? Yeah, right. If we had a this pixel's RGB value, then we have surrounding pixels. Maybe let's think, consider four pixels, left, right, up, and down, and then we can maybe think about the pixel differences. Okay, pixel differences between this lower part, upper part, L and R, and then the pixel difference will also be three-dimensional vector, and then we may have like a 4 additional set of three-dimensional vectors, right? So this is called a pixel difference, and also it is called a gradient as well. Okay, gradient. And what else? What else? What else? So it's a really embarrassingly simple idea, but typically when doing this image segmentation, the sum of the input feature for each pixel is just x and y coordinate index. Okay, so that way, so if we consider this image, so this one was maybe 480 and 640, and then the position of this pixel was maybe 30, 50, which means like a 30 is pixel and then 50 is pixel. And this pixel value, I mean pixel position itself, is used as a features. Okay, and then naturally, adjacent pixel will have a small difference in terms of those pixel position feature vector, right? So that way we can kind of encourage, like I said, the adjacent pixel will have a high similarity. Okay. Okay, then you can, use additional features like there are many other different, more advanced feature extraction methods, such as SIFT is also one method, and also histogram feature, like Hog feature. So all these are kind of image feature kind of extraction method that you might have heard that can be also computed for the features for each pixel. Okay, so that way you can design your feature vectors and then construct this kind of graph by using this kind of formula, and then apply the clustering algorithm, or this kind of spectral clustering algorithm. Okay, so far so good, right? So that way this normalized cut will generate more balanced clusters. Okay, now we we learn a little bit of graph theory. So the first one is this adjacency matrix, which is quite obvious. So we consider this a pairwise matrix, pairwise similarity matrix, or pairwise adjacency matrix. So in this particular graph, so somehow this 3 and 6 has no edges, which means they have zero similarity, or zero value as edge weight. Okay, so that way we only have the non-zero edges or non-zero edge weights in the corresponding pairs that have the edges. Okay, But what about this diagonal elements? So this is called a self edges. Self edges. Yeah, this is just a term in the graph theory. But this self edge is like this kind of edge, right? That pointing to itself. But in general, in most of the graphs, we set them as 0, assuming that there is no self edges. Okay, in this case, in the case of a undirected graph, such as a similarity graph that we compute using this measure, okay, this measure, and in this case, the edges from x2 to 4 or x2 to 3. So these the edges between these two will be the same as the edges from x3 to 2. Okay, so that way undirected graph and their adjacency graph will be symmetric. And then we can think about this additional matrix of degree matrix. So the degree matrix is just simply summing of either rows or columns and those values as setting those values as diagonal values in our square matrix. Quite simple, right? And degree matrix is, and also intuitively it is, yeah, just like a volume thing that we studied in the previous slide. We can consider from each particular node, we can consider the total sum of edge values and then set them as the diagonal, corresponding diagonal entries. So this is called a degree matrix. And in the case of an unweighted graph, so all these edges have just either connected edges or disconnected edges. So for example, like friendship networks. So we are either friends or not friends, right? So our Facebook's friendship doesn't tell you or doesn't say anything about how closely we are connected to each other, right? So in that case, edge weights will be either 1 or 0. In that case, what is the degree value of each node? It is simply the count or the total number of my friends, right? So that way, it is the number of edges that I have, and so it is called a degree. Okay, so we have a degree matrix and adjacency matrix A. And now the most important matrix today is this Laplacian matrix. So Laplacian matrix is subtracting from this degree matrix by adjacency matrix. It is quite simple. And on the diagonal, we have the degree values of each node, and on the off diagonal part, we have edge weight, but negative edge weight. Okay, negative edge weight because we subtracted adjacency matrix. Okay, it's quite simple, right? Degree and the adjacency matrix doesn't overlap at all, right? We just concatenate them, and then we just simply put the negative signs on all these those edge values which are located in the non-diagonal part. Okay, so this is our Laplacian matrix, and this Laplacian matrix has quite a number of interesting properties. Okay, so these properties are as follows. Eigenvalues of this Laplacian matrix are non-negative real numbers, and eigenvectors are real and orthogonal, and so on. So all these are from the linear algebra things, but I'll try to minimize those linear algebra contents. Yeah, because we had too much of a linear algebra in the previous lecture. Okay, so this Laplacian matrix can be also optionally be normalized by this degree matrix by multiplying d to the power of minus half on the left and right. So it can be it is changing this degree matrix so that they have all ones along the diagonal matrix, along the diagonal entry. So it is, yeah, I'm gonna just give a brief intuition about it. So in the case of social network graph, one really famous guy may have maybe several thousands of friends. Okay, several thousands of friends, but I'm a kind of a lonely person that doesn't have many friends. So in that case, I may have maybe tens of edges. So in that case, when running some algorithm, whether it's a clustering or yeah, maybe some rankings of some importance of nodes, and then those high degree nodes that have a lot of edges may influence our algorithm a lot more than those nodes that have very few number of edges. Right? So in that case, so one really famous guy that has maybe 2,000 friends, that doesn't mean that this guy has really close relationship to each of these 2,000 guys, right? So we can kind of discount them properly, right? So that the total time we spend with all our friends is kind of fixed. So in that case, we can kind of normalize their degree so that they have all the same degrees. Okay. So this kind of normalization can be done either by this or by this, or from both sides of left and right, we can normalize this Laplacian matrix in this manner. Okay, so it's like, yeah. So from here, yeah, it's not kind of, yeah, it may not make much sense because it's quite simpler case of undirected graph, but this representation can be used also for the directed graphs or directed graphs. So suppose we have this kind of edges, directed graphs. Maybe citation network may have this paper citing this paper, but this paper cannot cite this paper. So in this case, we can consider this kind of directed graph and their adjacency graph. So in this case, this yeah, so this is a Laplacian. So let's consider this adjacency graph. So in this case of an adjacency graph, and then x1 actually cited x3, and so we have an edge here, but x3 didn't cite x1, so we can have 0 here. So in this case, rows are corresponding to the node over from, and those columns are corresponding to like a 2 nodes and from node, or source node and target node. Okay, then if we yeah, so Laplacian is basically d minus a, and then suppose we compute, yeah, we multiply d inverse from right. So it's like normalizing each column so that their column sum becomes 1. Is it right? Right? So, so in this particular case, so we added them, and then that will be the first element in D. And D inverse is just element-wise inverse on these diagonal elements. And this total sum will be divided by each element in the first column. So that's what this multiplication on the right is doing, right? So multiplication diagonal matrix multiplied on the right will be doing the scaling on column-wise. So this we actually divide each element by their column sum, right? And so each column will become 1. So it means from the 2 node, each of the 2 nodes, their amount of received information is fixed as 1. Okay, so total edge weight, so sum of an edge weights as a target node is fixed as 1. So for example, this kind of directed edges are also used in maybe traffic graphs. So we have some junctions or some geographic point where where they are connected through some highways. So each highway is having some capacity. Okay, so one highway or one toll gate can have maybe at most 100 cars per second or per minute. Okay, in that case, they cannot incorporate more than 100 cars per minute. So in that case, we have to fix the total number of received information. So this is the normalization from the right. And in the case of this kind of normalization, the inverse on the left, in that case, when applied to the matrix A, then it is normalizing each row. It means as a source, you are sending the fixed number of an information for each node. Okay, it is like so you are one particular person, and then there exists some fixed amount of an hour that you are spending with your friends. So if you have one friend, and then you are spending maybe the total 10 times with that friends entirely. But if you have 10 friends, and then each friend you will only spend only 1 hour to each of your friends. Okay, so that way you can normalize from the source perspectives and also the column perspectives, and then this kind of thing, this kind of normalizing from both directions, from source and the columns, and halfways. Okay, halfways. So in this case, the diagonal values will become 1, but this guy and this guy will not be perfectly normalized as the total sum of 1, but that they are kind of normalized halfways, because we are only normalizing square root of the sum. Okay, it's a little bit conceptual kind of thing, but yeah, let's understand it that way. Okay, so so optionally we can do this kind of normalization process. And now we will learn about this important properties of this Laplacian matrix, which is D minus A. Okay, so this matrix L and this matrix L, and you consider some vector F. So you have 100 different nodes, and then L will be 100 by 100, right? And now you consider some matrix, some vector F, which is also 100-dimensional vectors. And you consider this F times L times, F transpose times L times F. And then first of all, what is the dimension of the resulting matrix? Would it be a column vector, a row vector, or scalar, or some matrix? It will be scalar, right? Scalar. And interestingly, this scalar is represented as this. Okay, so let me explain this. So yeah, F is a 100-dimensional vector, and so let's let's view this matrix L as just pure matrix, and let's start with the very simplest case of this matrix L, of identity matrix. So this is F transpose F and our matrix L, but let's just view that matrix as maybe C. And suppose C was diagonal matrix and also this identity matrix. And what will be the result? What will be the result? So the multiplication of the first two will be just F transpose, right? And then F transpose F will be just Fi, the squared sum, right? Okay, so it can be viewed as the 2 norm squared, right? So far so good, right? And now let's change this matrix C into a little bit more complicated form. Maybe 3, 2, 1, and so on. And how will that change the resulting representation? It will be 3 times f1. So this is a scalar, right? And 2 times f1. This is another scalar. Sorry, this is f2. This is f1 and f3 and so on. And here f1, f2 and so on. And it will be 3 times f1 squared, 2 times f2 squared, and the rest is the same, right? So we can view those values as just diagonal scaling from the original L2 norm, right? Right? Okay, then now the most complicated case where okay, let's just use maybe 3-dimensional case to just simplify the case. Okay, so we had 3 to 1, and then we understood the effect, and then I give you 5 here. And what is the effect of this 5? Okay. What is the difference from here? When having 5 here, and the rest of them is still 0. It is just a simple addition of one single term. And what will be that? 5, f1, f2, right? Okay, yeah. So, if we had maybe 2 here, and then plus 2 times f1, f3. Okay, so so if we have a symmetric matrix, so for example 5 as here as well, and this 5 is 5f1 f2, but we additionally have 5 f2 f1, right? So each element here, so suppose this element was Cij, and this Cij will be put together with Fi times Fj. Okay, so apart from this L2 norm or weighted L2 norm, we also involve this cross product within our vectors. If we have a 100-dimensional vector, in the case of normal typical Euclidean norm, we just squared the same value. We just take the square of the same value, and then we can consider the weighted version of it. But we consider the cross terms between f1 and f3, f2, 5, and so on. And then the corresponding weight values are determined or specified here. Okay? Okay, so far so good. And in this case, if we view this kind of representation, instead of using this general matrix C, we are plugging that matrix with this our special matrix of Laplacian matrix L. Okay, in that case, it will be Li comma j, which is I comma j's component of an L times Fi times Fj. So this is our this is the expression for this, right? So far this guy is just the same as this guy, right? Having this elements. Okay, in this case, L was D minus A, and Lij was if I are the same as J, and then Lij will become Dij, right? Or Di comma I, which is a diagonal element or the degree of i's node. And if I is not equal to J, and Lij will become minus Aij, right? Because in the case of off diagonal part, this guy will be the corresponding term. Okay. Okay. Okay, so this guy was this guy. So you guys understand this part. Then now we can represent. Yeah, let's try to manipulate this equation. So this guy is the same as this guy minus this guy. L was equal to D minus W, right? And then D was our diagonal matrix, and it can be represented in this manner, right? Because D is our diagonal matrix, where i's diagonal component is the degree value of each node, and that degree is represented as Di. Okay, and then this part is involving our elements in our adjacency matrix, which is corresponding to edge weight value, right? So what was our matrix A? A was just these values corresponding to these edges, right? Okay, so Fi comma Fj times Fj times Wij, right? And we have minus sign here, right? Okay. And now we represent this guy by just multiplying 2 on each side, and then we have 1 over 2. And then this guy is 2 times of this guy can be represented as this. And so the only difference is we change it the iterator. For I equals 1 through n became for j equals 1 through n. So they are essentially the same thing. Okay, so they are the same thing, and then we multiply this part by 2, so we have this. Okay, and then now this guy will have this part, because if we rewrite this part, then this part will be, so yeah, we just separate them into 2 parts. When I equals j or I equals not j. Okay, so in this case, when I equals j, then they are represented as this, because this guy is fi squared minus 2 fi fj plus fj squared, right? And then this guy times wij. Okay, so let's just manipulate the first term of I comma j. So it's actually double loop over I and j, and wij times fi squared. And let's change this as actually the double loop and I and j. And fi squared can be moved outside of the first loop because it's not dependent on j. And so is I and fi squared and j, wij, this, right? And this guy is like, so for fixed I, we iterate over all j and we add all wij when I is fixed, and that is the degree or the total sum of wij for a particular I, right? So this guy will become di, right? So di becomes this part, and so di times fi squared. So we obtain that, and so that will become this part. And similarly, if we incorporate this part and this, and now we change the order between them, right? And then the resulting part will become this, and then the remaining part will become this when I is not equal to j. So this part is simply decomposed into these three. So that way we derived this is the same as this, and this is the same as this. Okay. And now let's try to understand the meaning of this. So originally this guy is represented as this. Okay, it's a kind of generalized 2 norm. And that has different representation of this. And let's try to understand this. So it is, instead of using fi times fj, we now consider the difference between fi minus fj. So instead of just multiplying them together, we actually consider the difference between the two elements in our vector. Okay, and then we just multiply. We just take the square of it. Take the square of the difference, and then we give a weight of wi comma j. Okay, so means our so we consider the w, which is our adjacency matrix, and this value was 1.2, and this value was 0.1. Okay, and then our vector f was maybe 1, 2, 5, and this equation says between different I comma j, we take the difference. So between these two we have 1, and between these two we have 5, and we consider the difference between them. We consider the square of these differences, and then we just weigh these values by the corresponding edges. What was the edges between the node 1 and 2? It was 1.2. And what was the edges? What was the edge between 1, 3? And it was like 25. So we we give a weight of 0.1 to this guy. And yeah, we missed one thing, and the difference between the third and the second one was 3, and then 3 squared times, suppose this edge was 0.5, and we multiplied by 0.5. And we sum these 3 components all together. So that is the meaning of this. Okay? And then now, let's try to minimize this value. Minimize this value. One really simplest way of minimizing this value is by changing the vector f. So vector f of maybe 3-dimensional vector, and then if we just scale them down and down to have lower norm of this vector. So if this vector gets smaller and smaller in terms of length, and then regardless of wij, we can minimize this guy towards 0, right? If we just simply use a vector of all zeros as an f, and then this resulting value will become 0. So there's no point of minimizing. So let's consider additional constraints so that the vector length or the 2 norm or Euclidean norm is remaining as 1. Okay, so we fix the length of the vector, and now the question becomes more interesting, because in what direction of a vector, or what kind of vector, what kind of unit vector will minimize this representation? And that minimization will work as follows. So if we have a high weight, and then those 2 corresponding values should be similar. So what was the graph of this? So we have 3 nodes, and 1, 2, 3, and between 1 and 2 we have really strong edges. We have a really strong edge, and 1 and 3 we don't have a strong edge. only the strength of 0.1. And between 3 and 2 we have a like a moderate edge weight. Okay. And we consider the 3-dimensional vector, right, of an f, and between, for these 2 nodes that have a strong edge between 1 and 2, the first dimension and second dimension, the difference between those 2 values should be really small, right? And at the same time, between 1 and 3, since the edge weight is not that big, we are kind of okay to have a relatively large difference between these 2. Okay. So if we can minimize this by carefully choosing the vector f, okay, and then this vector f will be driven by your patterns in your edge weights. Okay, so this is the one of the key points.
아까 4일
네. 네. 그랬네요. 네. 여기가 네. Okay, so I was confused. So this guy should be 4 squared, right? 5 minus 1. Okay, and now let's consider the special case, because we are handling the clustering. And so let's think about some cluster example. So we have 7 nodes, and then what would be the ideal clustering pattern? So the clustering pattern will be like having the connection between the edges inside of each group, and no edges between different groups, right? So in this case, 1, 2, 3, 4, 5, 6, 7. And what will be the adjacency matrix, or what will be Wi, comma j? Our adjacency matrix A will have some diagonal elements, and the diagonal elements are block diagonal structure, not diagonal elements. So we will have all zeros. So we are considering matrix A, adjacency matrix. And what about the edges? So in the case of a simple form of unweighted graph, I mean whether we have a friendship or not. In that case, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? And 1, 1, 1, 1, 1, 1. And we all have 0 here. Okay? So this is an adjacency graph A. And then now let's go back to this definition. So here, you guys understand the meaning of this. And then now, even though we started from Laplacian matrix, these edges are only coming from our adjacency matrix. And now, so in this case, like a Li comma j times Fi times Fj and their summation over I comma j. But they are changed into Fi minus Fj squared, but instead of using Lij, we are only using Wij, the edge weights. Okay, and in this case, so we now consider the 7 different vectors. 7-dimensional vector of an F. And F transpose LF, which was sigma over sum over I comma j, Wij times Fi minus Fj squared, right? And then I want to minimize this, right? And then in this particular case of nicely clustered, or this kind of nice block diagonal structure of matrix A, and then I can make them perfectly as 0. And what will be that vector of making this value as 0? Okay, so just to simplify the situation, you can either put 1s or 0s. What will be the solution? Okay. How about this? In this case, can we make this guy as 0? Yes, because regardless of this, we have this part always be 0, right? So this is actually one trivial solution, and this is actually one global trivial solution that will make this guy as 0 for any type of matrix A or any type of adjacency matrix. And in this special case, there are some other vectors. So, right. So 1, 1, 1, 1, 0, 0, 0. So it means, so every pair, the difference was 0, and then this one will be always 0. But now, since we have this block diagonal structure, suppose, let's consider the first node and the fifth node. This guy and this guy. And clearly, the difference between the first element and fifth element will be 1. because 1 minus 0, right? And so in this case, it will create this 1 squared, which is a non-zero value. And this value is fortunately we multiply this value with the weight of 0, because wij or w 1, 5 will become 0. And where is w1, 5? It is this part, which is 0, right? And so here the point is, those values belonging to the same group, okay? The same group will have non-zero edges between them. So in that case, those parts should be 0, because it will be multiplied with the non-zero. But if the nodes belongs to different groups, and then we can make, we are allowed to use different values, because even though this part becomes non-zero, the weight value will become 0. Okay, and now the possible case will be 1, 1, 1, 1, 0, 0, 0. And what about the other case? The other case will be 0, 0, 0, 0, 1, 1, 1. Oops, right? And so these two vectors will create still this value as 0. And if we have 3 groups, and then we have 1s and 0s and 0s, 0s, 1s and 0s, and 0s, 0s and 1s. So that way we have more number of different vectors that are possible to make this value as completely 0. And those vectors or those patterns will come from the eigendecomposition of matrix L. And unfortunately the time's up, so I wish I could go a little faster, but I'll finish quickly in the beginning of the next chapter, and then next class, and then the next class we will start to study on D3 and the JavaScript development and programming. And probably I will send some homeworks, which is hopefully not that much. So please keep an eye on the announcements email. Okay, that's it for today. Thank you very much.
이게 지금 여기 안에 L이 지금 D-W도 근데 쪼개질 수가 있어요. 원래 행렬 성질 그렇게 해서
그러니까 D가 이제 L이 D-W잖아요, 데피니션이.
근데 쪼개질 수가 있어요.
그렇죠. 그러니까 A 플러스 B라는 매트릭스가 크게 있고 거기다 어떤 벡터를 더한다고 곱한다고 해봐요. 그럼 이거는 이제 분배 법칙이 적용이 되죠. 그죠? 그럼 여기서 분배 법칙이 적용된 것처럼 이 왼쪽에서 또 벡터가 또 곱해진다고 생각하면 또 분배 법칙이 또 적용이 되죠. 그리고 일반적으로는 이제 A 플러스 B라는 어떤 매트릭스가 있고 C라는 매트릭스를 그걸 더한다고 곱하면 이거 분배 법칙이 있어요. 이것도 똑같이